Okay, in this section, we are looking at the probability of independent events. So, all of these problems come from the Core Plus book that I don't really like, but I do like their probability stuff, so I'm going to use some of their stuff here. About half of U.S. adults are female, which we generally know, and according to a survey in USA Today, 3 out of 5 adults sing in the shower. So our first question that they ask us is, suppose an adult from the United States is selected at random. From the information above, do you think that the probability that that person is female and sings in the shower is equal to 3/5, greater than 3/5, or less than 3/5? So in this case, we know 3/5 of all people sing in the shower, but this person also has to be female, and only about half of those people who sing in the female who sing in the shower are female. So we should choose, this has got to be less than 3/5 here. So let's look at how we can find that probability. Alright, so let's use what is called an area model here. So we have here split up, let's pretend that this box that we see here is all of the people in the United States that we're talking about here. And half of them are male and half of them are female. And 3/5 of them sing in the shower. So I'm going to highlight those that sing in the shower. All these people right here say yes, they do sing in the shower. Well, in this case, we want to know the people who are female and sing in the shower. So we are looking at this section right here. Those are the people who are female and sing in the shower. So that's what we see. We've just done here. It says to fill in your area model. And then it says, what is the probability, in part D, what is the probability that an adult selected at random is female and sings in the shower? So in this case, we have 3 of those boxes highlighted. And there are 10 altogether. So 3 out of 10, or we could do a decimal, 0.3 for that. We're also asked, what is the probability that an adult selected at random is male and does not sing in the shower? So if we look here, male and does not sing in the shower, we're talking about these 2 boxes right here. And so in this case, our probability is 2 out of 10, which is 0.2. Okay. So area models can be helpful for something like this. Here's just another situation. Consider this problem. What is the probability that it takes exactly 2 rolls of a pair of dice before getting doubles for the first time? Explain why it makes sense to label the rows of an area model as shown below. And so we see here, we've got the first roll, we've got doubles and not doubles. The second roll, well, I think it kind of got cut off here. We've got doubles and not doubles. I think my picture kind of got cut off here. I think down here at the bottom it's supposed to say doubles and not doubles. I'm going to put an N for not doubles and a D for doubles. And let me, so we can see the whole thing. Alright, so whenever we're thinking about doubles, if you think back to that stuff that we've been doing, you've got 6 different ways that you can get doubles. 1 and 1, 2 and 2, 3 and 3, 4 and 4, 5 and 5, and 6 and 6. So you've got 6 ways out of 36 possibilities. So 6 out of 36 is 6. So you've got a 1 in 6 chance that you will get doubles each time you roll the dice. So that sort of explains why it makes sense to label our area model like this. Let's look at the next slide and we'll see what we're going to be asked for. We want to shade the squares that represent the event not getting doubles on the first roll and getting doubles on the second roll. So if we go back to our area model here, this column right here is our first roll. And so we want to not get doubles on the first roll and get doubles on the second roll. So in this case, for this, we would have, okay, for the second one, we're going to consider this problem. What is the probability that it takes exactly 2 rolls of a pair of dice before getting doubles for the first time. So here, we're going to label this area model here, and for A, we're supposed to explain why it makes sense to label the rows as shown, and then we also need to label the columns. So whenever you think about rolling doubles, if you think about those things that we've looked at, there are 6 different ways to get doubles. We could get 1 and 1, 2 and 2, 3 and 3, 4 and 4, 5 and 5, and 6 and 6. So there are 6 out of the total 36 possibilities for rolling the die. So 6 out of 36 reduces to 1 out of 6. So you see here one of those columns is, one of those rows is doubles, and then you've got 1, 2, 3, 4, 5. The other 5 are not doubles. So if we're going to label the columns here as well, I'm just going to use a D right here for doubles, and then an N in these columns. Ooh, sorry about this writing. An N in these columns for not doubles. Alright, so let's think about the situation. Let's look at the next question that we're asked. On your copy of the area model, shade the squares that represent the event not getting doubles on the first roll and getting doubles on the second roll. So, let me get my highlighter here. And not to doubles on the first roll, that is these. And then doubles on the second roll, that's right here. So we're looking for where those things overlap, and that is going to be in these parts right here. So for this, and C said, what is that probability? And so we have 5 out of the 36 possibilities. So the probability of not getting doubles on the first roll and then getting doubles on the second roll is 5 out of 36. Okay. The next thing we're supposed to look at is using that area model to find the probability that we'll get doubles both times. So if we go back to that area model, let's erase the one we just did. And oops, fix that real quick. Put that D back there. Okay, and so if we're looking here, doubles in both rolls, you've got here and here. You've only got one square where that overlaps. So your probability of getting doubles on both rolls is going to be 1 out of 36. And then you're supposed to use the area model to find the probability that you will not get doubles either time. So if we go back here, I'm just going to use a different color highlighter. So not doubles on the first roll and not doubles on the second roll as well. So those columns and rows overlap in this area here. So you've got a 5 by 5 area, so that's 25 out of 36. So you have a 25 out of 36 chance that you will not get doubles either time. Okay? Alright, now let's look at one where we're going to look at making our own area model. So we are looking at the probability that a child will or will not have freckles when each parent has one freckles gene and one no freckles gene. What is the probability that the child will not have freckles? And then don't worry about part B there. So here we're talking about freckles or no freckles. So I'm going to use a big F for freckles and a little f for no freckles. And this is a dominant gene situation here, like we've talked about. So we know each parent has one freckles gene and one no freckles gene. So we're going to use capital F for the freckles gene, and let's use a lowercase f for the no freckles gene. We've got capital F and then a lowercase f. So if both parents have this case, that means we've got a big F here, a big F, little f here, big F, little f here, and then 2 little f's. So assuming that this is a dominant gene here, that would mean if the child has the freckles gene, he or she will have freckles. So here, this square, and the square all represent a child with freckles. The two little f's would be the child that has no freckles. So the question says, what's the probability that the child will not have freckles? So in this case, that would be 1 out of 4. And then B's asking to get back something that we did. Okay, this is used a lot in biology. Okay, let's look at this next one because it's a little bit different. For A, about 25% of Americans put ketchup directly on their fries rather than on the plate. What is the best estimate of the probability that both your school principal and your favorite celebrity put ketchup directly on their fries? So assuming that your school principal, Mr. Hall, has nothing to do with your favorite celebrity here, these are independent events. So if we think of an area model for A, let me go back to where this is. Okay. An area model for A, we could make us an area model, and we have Mr. Hoyle. And up here we've got the celeb there. And there's a 25% chance that either one of them is going to put ketchup directly on their fries. So, right, we've got a 25% chance here. Let's go ahead. So 25% chance that each one puts ketchup directly on their fries, and then a 75% chance that they do not. So we want to know the probability that both of them put ketchup directly on their fries. So whenever we're looking at this, there's only a 1 out of 4 chance that the celebrity puts ketchup directly on their fries. There's only a 1 out of 4 chance that that Mr. Hull puts ketchup directly on his fries. So this square right here is the probability that both of them do. So for A, we would have a 1 out of 16 chance that both Mr. Hoyle and your favorite celebrity put ketchup directly on their fries. Let's look at B. Okay. So for B, this one's a little harder to draw because it says 84% of Americans pour shampoo into their hand rather than directly onto their hair. What is the best estimate of the probability that both your teacher and the President of the United States pour shampoo into their hand before putting it on their hair? This problem was made long before Donald Trump was president. It's a little bit funnier with him being president. So if we make ourselves an area model here, it's going to be a little harder to do. So here, the President, and then here we've got the teacher. So there's an 84% chance that President Trump puts shampoo in his hand before he washes his hair, and a 16% chance that he just squirts it directly onto his hair, which is weird, I think. But so I'm going to kind of split this right here, and right here I've got a 84% chance, and then here I've got a 16% chance. And then so there's also an 84% chance that I put shampoo directly into, or put shampoo in my hand before putting it on my head. And then 16% chance that I just squirt the shampoo right on my hair. So I want to know the probability that both of us squirt the shampoo into your hand before putting it on our hair. So in this case, I'm looking at this square right here. And if I want to know the size of that square, then this is an area model. So to find the area, we do the length times width of that box. And so in this case, the length is 0.84. And the width is 0.84. And so if we do 0.84 times 0.84, we are going to get 0.7056. So there is a little bit better than 70% chance that both your teacher and the President squirt shampoo into their hand before putting it onto their hair. Okay, so let's make some generalizations about this because we don't want to have to draw the area model for everything we do. So let's make some generalizations. The general rule for multiplication for independent events is if you want to know the probability of A and B occurring, assuming they are independent events, you just multiply the probability of A times the probability of B. In independent events, the second event does not rely on the first. So these were generally could be assumed to be independent events that we looked at before, assuming that Mr. Hoyle does not put ketchup directly on his fries because he saw his favorite celebrity doing so, or assuming that I did not find out that Donald Trump actually squirts shampoo directly onto his head when washing his hair, and I want my hair to be as beautiful as his. Assuming those are not connected, we can call these independent events. So this rule only works if the first event does not affect the second. So here I've put the outcomes for rolling our die again, our dice, and let's look at this situation. So we're going to suppose that Shiomo is playing a game in which he needs to roll a pair of dice and get doubles, and then immediately roll the dice again and get a sum of 6. He wants to know the probability that this will happen. So the first thing we want to know here is which option are we looking for. This P that you see right there with the parentheses means probability of. So option 1 is probability that he gets doubles on the first roll or gets a sum of 6 on the second roll. The So the second option is the probability that he gets doubles on the first roll and gets a sum of 6 on the second roll. And 3 is probability that he gets doubles and a sum of 6. So the correct answer here is option 2. For 1, it's or. So he could get doubles the first roll, but not get the sum of 6 on the second roll, and it would still satisfy this situation for option 1. That is not what the question was asking us. For option 3, it says the probability that he gets doubles and a sum of 6. So this would mean at the same time on the same roll, which is not what we're looking for. So we were looking for option 2, the probability that he gets doubles on the first roll and gets a sum of 6 on the second roll in separate rolls. And that will answer the question that they've asked us here. For B, we're supposed to explain why the multiplication rule can be used. So in this case, whenever you roll a pair of dice once, and then you pick them back up and roll them again, your first roll has nothing to do with your second roll. It doesn't change anything. So these are completely independent events. So we have already talked about the probability of rolling doubles. You've got 6 ways to get doubles out of 36, which reduces to 1 over 6. So our probability of doubles is 1 over 6. And then we'll know the probability of getting a sum of 6. So I'm going to flip back over here to my options for my dice, and I'm looking for all the combinations that have a sum of 6. So 1 and 5, 2 and 4, 3 and 3, 4 and 2, and 5 and 1 would all give us a sum of 6. So there are 1, 2, 3, 4, 5 different ways. So the probability that I get a sum of 6 is 5 out of 36. So if I multiply those together, I'm going to get 5 over 6 times 36 is 216. And if I change that to a decimal, just so it's a little easier to compare to other probabilities, I get 0.023. So a pretty small possibility that this would happen. Okay. All right. For 7, we're going to modify this game. This time, Shiomo needs to roll doubles, then a sum of 6, and then a sum of 11. We're going to find the probability that this sequence of 3 events happens. So in this case, we already said the probability of doubles is 1 out of 6. And we said that the probability of a sum of 6 is 5 out of 36. And then we are going to add that you have to get a sum of 11. There are only 2 ways to get a sum of 11. You can either get 5 and 6 or 6 and 5. So the probability of getting a sum of 11 is 2 out of 36, or we could reduce that to 1 out of 18. So if we multiply those together, we're going to get 10 out of 6 times 36 is 7776. We could reduce that, or let's just go ahead and get decimal for that because it's helpful. And if we get a decimal for that, we'll get 0.001286. So you can see that that small possibility went down even more by adding that third event in the sequence. So B says, suppose A, B, and C are 3 independent events. Write a rule for calculating P of A and B and C using probabilities of each event. So what they're wanting you to do here is the probability of A times the probability of B times the probability of C. Okay. And if you're wanting to do 4 independent events, well, then you've got probability of A times probability of B times the probability of C times the probability of B. So whenever you need to know the probability of a chain of independent events occurring, it's just a probability of 1 times the other times the other times the other. Okay. All right, so for each of the following questions, we're explaining whether it's reasonable to assume the events are independent. Then, if it applies, use the multiplication rule to answer. So A, what is the probability that a sequence of 7 flips of a fair coin turns out to be exactly HT, HT, T, H, H? So in this case, every flip of a coin is new. Every flip of a coin is independent. So this is independent. So you would have the probability of flipping a heads is 1/2. And then getting tails on the next one would be 1/2. And then you've got heads, tails, tails, heads, heads. So let's see, there's 1, 2, 3, 4, 5, 6, 7. So actually, let's just write this way. Let's write this. You would multiply 1/2 7 times. So we'd get 1, oh, sorry, it's hard to read. Let me try again. 1/2 to the 7th power. And if we do 1/2 to the 7th power, we will get 1 over 128. Or if you want to give a decimal for that, that would be 0.007813. Very small possibility that would happen. Okay, so if we look at B, we want the probability that a sequence of 7 flips of a fair coin turns out to be exactly all tails with 1 head at the end. So this is just the same as B because it's a different sequence, but it's the same probability because each time the probability of getting tails or heads is 1/2. So we get the exact same answer for B. Okay, for C, it says according to the National Center of Education Statistics, 27.9% of public school students live in a small town or rural area. If you select 5 students at random, what is the probability that they all live in a small town or rural area? So in this case, we're selecting 5 students at random. So the first pick does not affect the second pick or the third pick or the fourth pick. So in this case, there's a 27.9% that they live in a small town or rural area. So we would have 0.279, make it a decimal there, and we would multiply that by itself 5 times to see if they all live in that rural area. And so if we do that, 0.279 to the 5th power, we're going to get 0.001691. It's a very small chance that all 5 of them would be in a rural area. For D, it says the percentage of students who are homeschooled in the U.S. is 2.2%. If you pick 10 students at random in the United States, what is the probability that none of them are homeschooled? So in this case, we're again picking students at random. So this would be these would be independent events. Each student is picked randomly. So what's a little tricky about here, it says none of them are homeschooled. So that would mean all of them go to public school, or I guess private school, just not homeschool. So so here, what we would have to do is take 100 minus 2.2, and the probability that a student is probability the student goes to a school is 97.8%, or if we do a decimal, 0.978. So we would take that probability and raise it to the 10th power, and if we raise that to the 10th power, we are going to get 0.80055. And that's our probability that none of them are homeschooled, that all 10 of the students go to a school. For E, it says refer to Part D, you pick a family with 2 school-aged children at random in the United States. What is the probability that both children are homeschooled? Now, in this case, we are talking about something that is not independent, because we're going to pick a family with 2 school-aged children. So we've got all of the families in the country that have 2 school-aged children. We're going to pick one. What's the probability that both are homeschooled? This is not independent, because if one child is homeschooled, it is more likely that the other child is also homeschooled. Parents don't just randomly choose to homeschool. Typically, if they're going to homeschool, they homeschool all of their children. Not in every case, but it's much more likely. So for E, this would not be a case where we could apply the multiplication rule, because these are not independent events.